Hi everybody, in this video we're going to do IXL find the component form of a vector from its magnitude and direction angle. For some of the later problems we're going to be using this information over here to find the sines and cosines of special angles. I have them written out here, but we're not going to need this for a while. So let's look at the first problem. The magnitude of a vector z is 7. And its direction angle theta is 0 degrees. Write the component form for z. So you might remember that to find the horizontal component of a vector, we would just do the magnitude of the vector, in this case, the vector is called z, times the cosine of the angle theta. And to find the vertical component of the vector, we would do the magnitude of the vector times the sine of the angle theta. However, I'm not going to do that for this problem. I'm not going to do that for a bunch of these problems, actually, because this problem and a bunch of other ones are easy enough to solve graphically, which means we can just draw a quick sketch of what's going on, and we'll be able to figure out what the answer is. So if we just draw a grid over here and sketch what the vector z would look like. So we're told that it has a magnitude of 7 and its direction angle is 0 degrees. Well, this would be 0 degrees, 90 degrees, 180 degrees, 270 degrees. So a vector with a magnitude of 7 and direction angle of 0 degrees would look like this. Okay, so 0 degrees means it's forming a 0 degree angle with the x-axis, which means it's right on top of the x-axis. And a magnitude of 7 means that the length here is 7. So the components of this vector would just be 7, 0. Okay, it's completely horizontal. So if the magnitude is 7, then all of that magnitude is sort of in the horizontal component, and it's not moving up or down at all. So the vertical component would be 0. So that's it, and we're done with that problem. The magnitude of a vector c is 19, and its direction angle is 180 degrees. So 180 degrees means we're going over here, and the magnitude is 19. So imagine a vector which is 19 units long, but moving to the left because the direction angle is 180 degrees. The components of this vector would just be negative 19 for the horizontal component, 0 for the vertical component. Negative because it's moving to the left, 19 because the magnitude is 19 and it's completely horizontal. Imagine that you had a vector that also had a magnitude of 19. So it's just as long as this vector, but it was not completely horizontal. So let's say it looked something like this. So the length here, maybe I didn't draw it perfectly, but the length here is the same as the length over here. If that had been the case, then the horizontal component would not be 19 or negative 19. It would be somewhat shorter than that. And the vertical component would also not be 19. But since this vector is completely horizontal, then its horizontal component is the same as the vector itself. So the horizontal component is negative 19, and there is no vertical component whatsoever. So the vertical component is 0. Okay, the magnitude of a vector S is 15, and its direction angle is 3 pi over 2 radians. So I hope you remember radians. This would be, let me write the degrees and radians on this. So this is 0 degrees, 90 degrees, 180 degrees, 270 from here all the way around to here is 270 degrees. So that's degrees. In radians, this would also be 0 radians. 90 degrees is the same as pi over 2 radians. 180 degrees is the same as 2 pi over 2 radians, or 2 pi over 2 is just pi, so pi radians. And 270 degrees would be 3 pi over 2 radians, so like that. Okay, so we're talking about a vector here which is pointed down like this. Okay, so the direction angle is 270 degrees, or 3 pi over 2 radians. So which means that the vector would be pointed down and the magnitude is 15. This vector here has no horizontal component. So the horizontal component would be 0. The vertical component would be negative 15. Okay, so when you have a vector which is completely horizontal or completely vertical, then the magnitude would go in the magnitude would be the same as one of these components, except possibly negative if it's pointed down or to the left. Okay, let's continue. The angle is 0 radians and the magnitude is 12. So that would be, since the direction is 0 radians, that would be a vector pointing like this. So it's completely horizontal and it's moving in the positive direction. So the horizontal component would be positive 12. The vertical component would be 0. Another 3 pi over 2 radians. This is the same thing, just using the IJ notation instead of the angle bracket notation. For this one, the vector would be pointing down. So it has no horizontal component. And the vertical component would be negative 2. Okay, the magnitude of this vector is 2. Since it's pointing straight down, then it would have a vertical component of negative 2, or negative 2j. All right, let's do one more like this, and then we'll jump to the next level. 180 degrees, maybe one with radians, I don't know. Because we did one that was horizontal, that was 180 degrees. Okay, so anyway, now we have 45 degrees. You know what? Let me get that grid back. Okay, so the magnitude of vector C is 3, and its direction angle theta is 45 degrees. So it's not completely horizontal. It's not completely vertical. 45 degrees would make it look like this. Okay, this is a 45 degree angle. Okay, and the magnitude is 3. So does this mean that I should write 3, 0? Or maybe I should write 0, 3? Or perhaps I should write 3, 3? Actually, all of that is incorrect. We can do that if it's completely horizontal or vertical, but not if it's diagonal like this. Because if this is diagonal, then the horizontal component, if this has a length of 3, then the horizontal component would have a length which is somewhat less than 3. Same thing for the vertical component. This arrow is shorter than this arrow. So neither one of these components are 3, and neither one of them are 0 either. So how are we going to figure out the horizontal and the vertical components? Well, we're going to go back to that rule that says if we want to find the horizontal component of some vector, I'm just going to call the vector V, even though I know it does say C over here, because I'm just going to keep this on the screen for a while. I don't want to keep changing it. Then it would be the magnitude of the vector times the cosine of the angle. And to find the vertical component, we would need to do the magnitude of the vector times the sine of the angle. So in this case, let me just erase this so I have room to write. In this case, the magnitude of the vector is 3. We're going to multiply that by the cosine of 45 degrees. Cosine of 45 degrees, I have it all over here for you. You can write that down or take a screenshot. Cosine of 45 degrees is 1 over the square root of 2. So this would be 3 over the square root of 2. Now for the vertical component, we have the magnitude of the vector, which is still 3, times the sine of 45 degrees, which I have right here. That's also 1 over the square root of 2. So both of these would be 3 over the square root of 2, except I believe that IXL would not accept this, if I'm remembering correctly from another IXL exercise, maybe like a month ago or something. To rationalize the denominator, we could multiply the numerator and the denominator by this denominator over here. If we multiply the square root of 2 by the square root of 2, then that would give us 2. The square root of 2 times the square root of 2 is just equal to 2. But if we multiply the denominator by that, we have to do the same thing in the numerator. Okay, so in the numerator, we're going to get 3 times the square root of 2, which we're just going to write like that. Okay, and this, of course, would be exactly the same because these are the same. So both of these components are going to be 3 times the square root of 2 over 2. I think you could also do 3 divided by 2 is 1.5. I think it would also accept 1.5 times the square root of 2. Let's write it this way. Okay. So the I didn't want to erase that whole thing. I want to keep this. Okay, the magnitude of a vector x is 6, and its direction angle theta is pi over 3 radians. Write the component form for x. Okay, so the magnitude is 6. I have a v here instead of an x, but whatever. So we're going to write 6 times the cosine of pi over 3 radians. So what I have in this column over here is all radians, by the way. In this column, it's all degrees. The cosine of pi over 3 radians is 1/2. So 6 times 1/2 is 6 over 2, which is 3. So the horizontal component is 3. And the vertical component would be the magnitude, which is 6, times the sine of pi over 3 radians, which is the square root of 3 over 2. So this is 6 times the square root of 3 over 2. 6 divided by 2 is 3, so we would get 3 times the square root of 3. That's the vertical component. All right, this one's basically the same. Let's skip a level here, see if we get anything different. Okay. Yes, so for this problem, we're going to use this formula again. So the magnitude of the vector is, oh, they gave me a v here. That's good. The magnitude is 2, so we'll write 2 over here times the cosine of 4 degrees. And for the vertical component, we want the magnitude 2 times the sine of 4 degrees. So for this one, these 4 degrees is not one of the angles that I have over here. For this one, we're going to want to use a calculator. So let's just go over to desmos.com/scientific, and we're going to be rounding this to the nearest 100th, okay? So we can type all of this into the calculator actually. 2 times the cosine of 4 degrees. Make sure your calculator's on degrees and not radians. Unless they give you a radians problem, then make sure that it's in radians. So 2 times the cosine of 4 degrees to the nearest hundredth. Oh, okay. So this is the hundredths place right over here. 2 decimal places, 2 places after the decimal point. That's the hundredths place. The next digit over is a 5. So that means that this should get bumped up by 1, which would make it a 10, which means we would put a 0 here and carry the 1 over to here. 9 plus 1 is 10 again. So we would have a 0 here and carry the 1 over to here. 1 plus 1 is 2. So we're going to get 2.00 for the horizontal component. And for the vertical component, we would need to do 2 times the sine of 4 degrees, which rounded to the nearest hundredth would be 0.14, because that 9 is going to bump the 3 up to a 4. Remember, anything 5, 6, 7, 8, or 9 would bump this digit up 1. 0, 1, 2, 3, or 4, we would keep this digit the same. Okay. Oh, what did I just say? 0.14. Okay. All right, let's do one more like that. Actually, really, there's no point in doing another one like that. It's exactly the same. So for the horizontal component, we would just have 6 times the cosine of 5 degrees. And for the vertical component, we would have 6 times the sine of 5 degrees. And you can use the calculator to work that out. Let's skip a level, see if we get anything different here. This is the exact same question we got before. Let's skip another level. Okay, the magnitude of a vector y is 11 and its direction angle is 135 degrees. This is exactly the same as before. Maybe the only difference here is that for the horizontal component, it would be a negative number, because if we sketch it real quick, 135 degrees is about here. So we can see that we're going to get a negative horizontal component and a positive vertical component. But we could do this very simply in the calculator again. We're just going to do 11 times the cosine of 135 for the horizontal component. And we're going to do 11 times the sine of 135 for the vertical component. Okay, for the horizontal component, we're going to round that to negative 7.78, because this 8 is going to bump up this 7 over here. So negative 7.78 for the horizontal component, and 7.78 for the vertical component. All right, and let's just make sure that that's reasonable. If I have a vector that looks like this, and the magnitude is 11, then the horizontal component would be, first of all, negative, and second of all, the length would be a little bit less than 11, right? 7.78 seems reasonable for the length of this vector, and also the length of this one. The lengths happen to be the same. All right, so it does seem like a reasonable answer, right? Oops. Oh, what did they say? Oh, okay, yeah. So write each component in exact simplified form. Okay, so you got to be careful. So here's how we should have. By the way, this is not wrong what I said. It's just not in exact simplified form. If you do 11 times the square root of 2 and then divide it by 2, you would get 7.78 approximately. All right, so you do have to be careful and pay attention to when it says write each component in exact simplified form. I was not careful that time. But here's how we can think about this problem. So the direction angle was 135 degrees. That is not one of the special angles which I wrote over here. All I wrote was 30, 45, and 60. However, 135 degrees is equal to 90 degrees plus 45 degrees. Okay, so 90 degrees from here to here and 45 degrees from here to here. Do that in a different color. Okay, this plus this would be 135 degrees, okay, where this vector is. Now, if this is 45 degrees, then what is this angle over here? What is that angle? Well, I know that this is a right angle, which means that from here to here is 90 degrees. So if this is 45, then this must also be 45, because 45 plus 45 is 90. Okay, so with a little bit of geometric thinking over here, we can realize that the special angle which we want to look at from this list is actually 45 degrees. Okay, now let's go back to the, you know what, this is getting very messy over here. So we want to be looking at 45 degrees. Where do I have space to write this? So the magnitude was 11. So if we do 11 times the cosine of 45 degrees, then that would be 11 times 1 over the square root of 2, which is 11 over the square root of 2. If we do 11 times the sine of 45 degrees, then that would also be 11 times 1 over the square root of 2. Okay, so at least the absolute value of both of the components is going to be the same. You'll see why I said absolute value in a second, because one is going to be positive and one is going to be negative. But there's no need for me to write this twice, so let's erase that. Okay, so I have 11 over the square root of 2. In order to rationalize this denominator, we don't want an irrational denominator here. We're going to multiply the numerator and the denominator by this denominator here. Okay, just like we did a couple problems ago. And the square root of 2 times the square root of 2 is 2. 11 times the square root of 2 is 11 times the square root of 2. We'll just keep that the way it is. So you can understand why it says 11 times the square root of 2 over 2. Okay, so we just worked that out. How can you figure out that this one is supposed to be negative and this one is supposed to be positive? Well, you'd have to sketch a graph of the vector. So if you know that this is 0 degrees, 90 degrees, 180 degrees, 270 degrees, 135 degrees, which was the direction angle that was given to us in the problem, would put this vector over here in the second quadrant. I don't know if you remember from another video that this is the first quadrant, this is the second quadrant, this is the third quadrant, this is the fourth quadrant, okay? So if we have a direction angle of 135 degrees, then it would be somewhere in this, the vector would be in this area, right? Which means that the horizontal component would be negative and the vertical component would be positive. So that's how we know to put a negative here and a positive here. Okay, so let's move on. Let's check first of all to see, okay, it says to the nearest hundredth. It doesn't say to put it in exact simplified form. So for this one, we're just going to do 2 times the cosine of 173 in the calculator. And 2 times the sine of 173. All right, and then rounded to the nearest hundredth, this would be negative 1.99. This would be 0.24. Okay, so I'm just going to end the video there and have a great day.